start off this section, I want to look at R2 and R3. So I have them drawn out here. And for each one, I've also drawn out a special set of vectors in that space. So in R2, I have the vectors I and j sketched out. In R3, I have the vectors I, j, and k sketched out. Now, we know that these vectors in each space have some special properties. In each case, the set of vectors are linearly independent, and the set of vectors span the whole space. So I and j in R2 are linearly independent, spans the whole space. In R3, I, j, and k are linearly independent, and they span the whole space. So that means these vectors form a basis for each of their respective spaces. Okay? Now, those two properties, we've looked at this before, and we've looked at other bases for vector spaces based on this idea. So a basis, recall that a basis for a vector space V is a set of vectors S in V so that two properties are satisfied. One, that the span of those vectors of S equals V. It spans V. Set of vectors in S span V. And two, the vectors in S are linearly independent. Okay, and we used these vectors, these examples, as kind of the examples to kind of formulate this idea. We noticed that the vectors I and j in R2 they span the whole space, they're linearly independent. In R3, I, j, k span the whole space, they're linearly independent. And we notice that there's other sets of vectors that have these same properties. But vectors I and j, they're more special than that. These aren't the only two properties they have. They don't just span all of R2. They're not just linearly independent. They have some additional properties that make them useful. In particular, these two vectors are orthogonal to each other. They meet at a right angle. And also, they are unit vectors. They have length 1. The same thing is true for the vectors in R3, the standard basis in R3. I, j, and k are each orthogonal to each other. Okay, they're each orthogonal to each other, and they're each unit vectors. Those extra properties, not just that they're a basis, but that they are an orthogonal set of vectors and that they are all unit vectors, they actually lead to some very nice properties. So just like before when we defined a basis generally, we also want to see if it's possible to extend these other nice properties. The fact that the vectors are orthogonal and that they're all unit vectors. What happens if we extend those ideas to other sets of vectors? So that leads us to the following definition. So let's let V1, V2, all the way to VK, let's let that be a set of non-zero vectors. Okay, we call this set an orthogonal set if the dot product between any two different vectors V is 0. We do emphasize that I has to not be j, so we're not taking the dot product of a vector with itself. But any two different vectors, if we take their dot product, it would be 0. So like v1.v2 would be 0. Also v2.vk would be 0. Any two different vectors in this set, they're going to be 0. And remember, if the dot product of two vectors is 0, that means they are orthogonal. They will meet at a 90-degree angle. Okay? So we call this set of vectors an orthogonal set of vectors. Notice that's exactly what's happening up here with our standard basis vectors. If we look at R3, for example, if I take the dot product of I with any of the other two vectors, the dot product will be 0 because they are orthogonal. The same is true with K. The same is true with J. Okay? So these would form an orthogonal set. Moreover, if, in addition to being orthogonal, the lengths of all the vectors are equal to 1, so they're all unit vectors, we say the set of vectors is an orthonormal set. Okay? So if all the vectors are orthogonal to each other, it's an orthogonal set. If all the vectors are orthogonal to each other and they're all unit vectors, we call it an orthonormal set. All right? Let me give you an example. Very small example, very quick example. Let V1 equal 1, 1, and V2 equal negative 1, 1. Then the set with vectors V1, V2 is an orthogonal set. Since if I take the dot product of the only two different vectors in the set, V1 with V2, I get what? 1 times negative 1 is negative 1, plus 1 times 1, that gives me 0. They are orthogonal. They meet at a 90-degree angle. Okay? Notice, so that this would not be an orthonormal set, because V1 and V2, neither one of them are unit vectors. To be an orthonormal set, the vectors would have to be orthogonal and also be unit vectors. But if we have an orthogonal set, we can easily fix that because it's easy to normalize a vector. It's easy to take a vector and turn it into a unit vector pointing the same direction. We can easily turn this into an orthonormal set by normalizing the set. Okay, so let's start with V1. I'm going to call my new normalized vector U1. So I'm going to take V1, and to normalize it, I just divide by its norm. Okay, so the norm of V1 is going to be square root of 2. And so I get 1 over square root of 2, 1 over square root of 2. And similarly for U2, I'm going to let U2 be my normalized vector V2. So V2 over the norm of V2. V2 was the vector negative 1, 1. And the norm of vector V2 is again square root of 2. So I get negative 1 over root 2 times 1 over root 2. So thus, the set of vectors U1, U2 is an orthonormal set. Because since I normalized them, I preserved the same direction, which means they're still orthogonal, right? They still are 90 degrees to each other. But I change their length into a unit vector. So these are orthogonal vectors that are each a unit vector, and therefore it is an orthonormal set.